Great. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for today. Again, Lord, I thank you for these students. We thank you for your grace, and mercy, and love for us each and every day. We thank you that you're an awesome God, that you loved us even when we didn't love you, Lord Jesus. I just pray be with us today. Help us to glorify you again, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, let me just walk through the homework for a minute here. I think everybody will be able to do number 77, number 78. How do you do number 79? What do you got to do? You got to calculate the integral of x squared plus y cubed over the square, and then you have to divide by the area of the square, which is 1. I really should have done this on like 0, 2 to 0, 2 to make sure you understood what you were doing. Obviously, we can't grade the answer. We'll have to grade your work. So make sure it's indicated in your work that you're dividing by the area. Oh, who am I kidding? The grader's not going to be that careful. But you should keep in mind that when we calculate the average, we have to divide by the area, right? Number 80, there it's critical that you draw the picture, right? So that you can reverse the bounds and do the integral. Did I work this in class? I worked one an awful lot like it, but not the specific problem, very, very similar. Let B be the solid region bounded by x equal to 0, y equal to 0, z equal to 0, and the plane 2x plus 3y minus 3z equals to 1. All right, so basically you've got this solid region in the first octant, I believe, and that'll take you a few minutes to do. Takes me about 20 minutes to work that problem carefully. 82. Let R be the regions in quadrants 1 bounded by blah, blah, and blah. Calculate that integral by changing to polar coordinates. So, does that make sense? Quadrant 1. Yeah, so we've got unit circle. Circle of radius 2. Right? Y equals x. Well, y equals 3x. We're also told that it is in quadrant 1, right? So that limits our over here, right? So basically that's this. We're doing the integral over this sector right here, right? Can you get that in the, yeah, okay. Is it okay? Maybe I can turn on the lights and, I'm going to turn on the lights just to make sure we can see the board, but then I lose this, but oh well. Anyway, this is what Mission 6, if you're following along online. It's posted in the website. All right, so what would you integrate from? R is going from 1 to 2. What's the range for the theta? Pi over 4, I can get. Yep. Tangent theta is y over x. So if you want to figure out the theta from the line y equals to 3x, that's just 3x over x, right? 3. So we can just say theta is inverse tangent of 3 for the upper theta, right? Whatever that is. I mean, maybe it's not something pretty, I forget.
If it's not pretty, we can do it in inverse tangent of 3.
I mean, I think if it's not pretty, you could leave it like that, or maybe it'd be better to, yeah, you can leave your answer in terms of inverse tangent 3, unless it's something. Let me check for a second here. 1.2490, doesn't ring a bell. But then again, yeah, square root of 3 would have been, yeah, okay. That would be what, pi over 3? Okay, so anyway, that's clear, yeah? I mean, you could also leave your answer as a decimal on that problem if you wanted to. I think that would be reasonable. That's actually a good point. What should the answer be? We're calculating a double or a triple integral. What is the answer? Is it a function? Is it a vector? It's a number, right? Yeah, it's a number which represents either a mass, a charge, a volume, an area, something like that, right? '83. Find the volume bounded by the cylinder. And those two things, so you want to use cylindrical coordinates there for sure. And basically your r is going to go from 0 to 1, and your theta is going to go from 0 to 2 pi. And what's z between for problem 83? Z goes from 1 all the way up to 2 plus r cosine theta plus r sine theta, right? That's kind of like the one I did yesterday. Problem 84 is quite obviously a what? That's a spherical. And that looks kind of nasty because you've got this e to the minus rho cubed. You're like, I don't know how to integrate e to the minus x cubed, right? But remember, dv pops on out a rho squared for you, so you can do a u substitution. U equals to minus rho cubed will make that one work out quite nicely. Find the centroid of the region bounded by blah and blah. Now that's actually going to take some thinking. Oh, we did, though. Maybe that was the day everybody was gone. You were there? Ah. Shh. I can say we covered everything on the day everybody was gone. Don't let them know. I guess they could have watched, but I don't know. Yeah, we'll talk about centroids here in a minute. Let me just get through this real briefly. Is there anything else in here that you have questions about before I put it away? You'd like to see some centroids. What else? It's almost that. It's almost that. There's another trick with the Jacobian I should share with you that may be relevant to that problem. I forget. Use the Jacobian to relate the volume element du, d phi, d theta to Cartesian volume and dy dx dz, given that. You're talking about 89, right? U equals cos cosh sine cosh u sinh. All right, yeah. And I should work a problem like number 88, I think. We haven't seen one of those yet, right? Okay. So here's an example, which this example 6.6.11, I have us calculate the volume and center of mass of region E, which is basically below the cone above the cone z is equal to the square root of x squared plus y squared, and below the sphere x squared plus y squared plus z squared equals 1. Basically, this is like a snow cone. Right, so I want us to find the center of mass of height 1, yeah, and 45 degree. But so the basic thing is to find the centroid, all right? Or so what is the difference between centroid and center of mass? Center of mass is what you do is you integrate the mass density over the volume times x, right? Divide by the mass. This gives you the x coordinate of the center of mass. This gives you the y coordinate of the center of mass. This gives you the z coordinate of the center of mass when you do these triple integrals over the volume in question. Yeah.
So what is mass, though, in just a graph?
What is what?
We're not given a mass.
We're given a density function. The density is the mass per unit volume.
But just an equation doesn't give us the mass.
Well, the mass is the integral of the infinitesimal mass over the volume which you can actually calculate by doing the triple integral of the density over the volume. Now, if the density is a complicated function, it's not directly related to the volume, right? But if it's constant density, the relation between the density and the volume is just density times volume gives you mass.
I think what he's trying to say is like in problem 85, we're not given a density.
We kind of relate physics concept of mass to this complicated expression. I don't see where in that expression.
I'm getting to that. The centroid, all right, is not the center of mass. Well, centroid is something geometric, right? So imagine that the shape has constant density, right? Then the centroid is the center of mass with respect to that case. It's like the geometric average of the shape. So essentially you could just set the total mass equal to 1 and the density equal to 1. Well, excuse me, you can't set, I mean, you could set the total mass equal to the volume, is what I'm saying, in those formulas we were just looking at. Tell you what, let me put this away. So just to reiterate, the total mass is the sum. It's the sum over the masses, right? This becomes the total mass is equal to the triple integral over dm, which you express as the triple integral over the density times dv. The center of mass vector is 1 over the total mass, and then what you do is you do the sum over m sub I, the ith position vector, I equals 1 to n, right? Now that, when you look at it in x coordinates, it gives you, the x center of mass is 1 over the total mass, the sum of m sub I, x sub I. And the y center of mass is 1 over the total mass, the sum over m sub I, y sub I. And the z center of mass is 1 over the total mass, the sum over m sub I, z sub I. So when you pass to integration, when you pass to a continuous medium rather than a discrete medium, then these sums become integrals, and you're just left with the center of mass for x is 1 over the total mass, triple integral over the volume that you're interested in, the density, x times dm. But instead of writing dm, we don't really know what that is. I mean, that's a mnemonic for what I'm writing now, which is that we're just integrating x times the density, the mass per unit volume, times dv, because we know how to do the volume integral. And likewise, the center of mass for y, I'll just jump straight to y delta dv, and the center of mass for z, 1 over m, the triple integral of z, the density dv. Yes, okay. So let me just make a conclusion, then answer the question. Center of mass of volume, let's say B with density delta, which is a function of x, y, and z, okay? Generally speaking, is x center of mass, y center of mass, z center of mass, all right? That's just a definition, essentially, for us in here. I tried to give you a little bit of the flavor of how it's motivated physically from the finite case, but, that's just a motivation. This is actually what you do in terms of the calculus here. Our second definition is that the centroid of B is the center of mass where the density is just set equal to 1 for all points in D, okay? That's the relation between these things. Centroid is just a geometric thing. But anyway, now that I got that out of my system, those are the definitions for volumes. So what's your Well, let's take a sphere, all right? And suppose this sphere is something like the density as a function of volume is equal to, let's say, k times rho, where k is some proportionality constant, right? So that's kind of a weird thing. It's like it has almost zero mass at the center, and then it gets more and more massive as you get to the edge, right? So what would the mass of this be? See, this is the mass per unit volume, right? So to calculate the total mass, I have to simply calculate the integral. Well, I would just say integral of dm. But how do you calculate that? You calculate the triple integral of k rho dv. And, I'm supposing that this is a sphere, say, of radius r. Well, then I know what to do, right? I just go, okay, well, hey, that's k times the integral from 0 to 2 pi, integral from 0 to pi, integral from 0 to r of rho squared sine phi d rho d phi d theta. Oops, not rho squared, but rho what? Y cubed, yeah. Remember dv is rho squared sine phi d rho d phi d theta. In sphericals, that's the Jacobian element. It's just that.
So when the density is 1, then you just take the triple integral 1 dv.
Yeah. I mean, or if the density is just constant, you end up with the density times the volume gives you the mass.
So since it's asking for the centroid, we assume the density is 1.
Right, in that homework problem. Now this what I'm about to integrate here actually has a special significance in and of itself. Since we're on it, I'll mention it. This is actually the solid angle of the sphere, which is 4 pi. So that would be the mass in this case. What do the units have to be on K? Something like kilograms per meter to the fourth, right? See, because the original formula should be kilograms per cubic meter, so
Or just for the final one.
yeah,
For the final one.
right. Now I can tell you what the center of mass is for that ball without doing calculation. It's still the center. It's got a spherical symmetry, right?
Yeah, the problem was just that I knew the formulas that you gave us with the mass, I just didn't know where that would be given.
No, it depends on the shape, right? Yeah,
Yeah, it does.
yeah, for sure. Mm-hmm. Now, what would the center of mass and centroid be for an area? I mean, I did it for a volume, but you guys were asking me a homework question about an area. You're like, what's gives, right? Well, of course, for the area, you just erase this, maybe one of those. Yeah. Mr. Gibson has a point. Yeah, I regret that. Now, we will also be able to talk about, you see, there's this notion of center of mass and centroid. It's an interesting question for almost every kind of integral we study in this course. It's an interesting thing for the double integral. It's interesting for the triple integral. It will also be interesting for the surface integral and for the, I mean, we'll later ask the question for like a curved surface, right? For a curved surface, where is its center of mass, or where is its centroid, right? Or how about this for some space curve? Where is its centroid? Or for some kind of, well, that's about it. But we can also talk about the center of mass and centroid for those objects once we have the appropriate integrations to work with, which we will a little bit later, but not too long from now. All right, let me see if I can't find a good problem to work for you guys. Just a second here. Oh. Uh-oh. Right. Well, I didn't erase it, so it'll be back. Sorry. There's a couple of fun examples. Oh, come on. Come back to us. What? Hey. What's the deal? It's weird. Oh, okay. Allow me this moment of leisure, and then we will get back to our double integral that I owe you. So if you have a volume bounded by x squared plus y squared equals to r squared in 4 dimensions, that means that there are 2 other directions, right? So there's the circle and then 2 other orthogonal directions that are unbounded. Like a regular cylinder, you've got x squared plus y squared, so you're stuck between x squared plus y squared equal to 1, right? And then you can just go up and down in the z, right? But in this hypercylinder, you can go up and down in the z, but you can also go up and down or right and left in the w without leaving the cylinder. Of course, we can't picture this directly, but we can calculate its volume, provided I bound the cylinder between 0 and h for both of the z and the w. So it's pretty cool. I just calculate the 4-dimensional volume, which changed to cylindrical coordinates with 2 z's, so to speak. Z and w are both like z. So I have to integrate r d theta dz dw over the appropriate range, which would be 0 to h, 0 to h, 0 to 2 pi, and 0 to r. And out pops pi r squared times h squared. It's pretty cool. I mean, I don't know. I'm kind of happy with it. It's kind of like, I don't know. I don't know how to I can't visualize it, but there you go. There's the volume of a generalized cylinder. And then this example here, I take basically and look at a bunch of spheres, right? A bunch of spheres, one at each value of t, in the hypervolume of that, whatever you'd call that. Anyway, the hypervolume of a solid sphere attached at each t along 0 to h ends up just being h times the volume of a sphere. It's kind of like the analog of the volume of a regular cylinder of height h just being pi r squared times the height, right? So if you have basically a cylinder of spheres, it's a stack of spheres rather than a stack of circles, it's still just h times the volume of the thing being stacked. So the volume of a cylinder is h times pi r squared. The volume of this thing is 4/3 pi r cubed times h. But I don't know. There's something interesting, the fact that we can calculate things we can't visualize, right? I don't know. By the way, I would just draw your attention. You can check your answer to that last problem with the 5 bonus points right here. It's in the notes. See? If you hadn't noticed already. X squared plus y squared plus z squared plus w squared equals to r squared. I used r instead of rho here, right? But that Jacobian, that awful 4x4 Jacobian, should break down to rho cubed sine squared alpha sine phi in our notation from yesterday, as it happens. All right? Okay. Any questions about this stuff? Probably not. Let me go back to the easier stuff. I hope you think I have enough examples in these notes. I think I have enough examples in these notes. My goodness. Come on. You know, I brought this, finally. Sorry, I get a little bit brain dead this time of day. So I have 3 things I want to do today before we're done. I want to show you the other fun fact about the Jacobian. I want to give you at least one decent polar integral example, and I want to show you the substitution problem, which is maybe not as obvious as some of the other ones we've worked. Let's see here. Let's start with the Jacobian. Let's see here. So, if you allow me this notation for a second. This would be what? This is the determinant of xu, yu, zu, xv, yv, z, v, xw, yw, zw, right? What would it mean if I instead asked what's partial of u, v, w, x, y, z? I probably should absolute value, right? So this would be what? Ux, uy, uz. Ux, vx, wx, uy, uy, vy, wy, uz, vz, wz. So this would be like the Jacobian of the transformation versus the Jacobian of the inverse transformation. How are these related? It's really this. Sorry. So this follows from the chain rule of multivariate calculus. I mean, we could prove this in advanced calculus or something, but that is in fact true. So, application of this formula. Let's see here. We calculated, remember we calculated partial x, y, z of partial rho phi theta was what? I guess I can drop the, if you don't, I keep putting absolute value bars on everything. Let me just, whatever. All right. Oh man, what have I done? Ah. This was equal to what was it? Rho squared sine phi, yeah. So if I was asked to calculate this, the answer would be yes. that might be very helpful to know if it's not fun to solve for the variables, right? Like, for example, if I'm given x is equal to u squared plus v squared, and if I'm given that y is equal to v squared plus w squared, and if I'm given that z is equal to uvw, and somebody asks me to calculate the Jacobian of uvw xyz, I say, first of all, you jerk. Why? Why would you do such a thing? It's an evil question. If you don't know about this, it's an evil question, because in order to actually do that calculation, you'd have to first solve for u, v, and w as functions of x, y, and z, which is not altogether pleasant, right? But it's easy to calculate this, right? That's just the determinant of what? 2u, 0, vw, 2v, 2v, uw, a 0, 2w, uv, which you could calculate. If that's actually your homework problem, I'd be annoyed. I just made this up. Yep.
Where did you get v squared sine theta?
Oh, that was like a 20-minute calculation we did the other day. That's because if you calculate, this is the determinant of like cosine theta, sine phi, sine theta, sine phi, cosine phi, sorry, processing, rho minus rho sine theta, sine phi, rho cosine theta, sine phi. Oh, I was doing phi, wasn't I? Sorry. Cosine theta, cosine phi, rho sine theta, cosine phi, minus cosine phi, minus sine phi rather. And then the other one. That worked out to rho squared sine phi yesterday. We had sine squared plus cosine squared. It happened like 2 or 3 times. It collapsed down to this. Right? Every time we do the spherical change of variables, we're using this. In fact, I use that identity in order to do this here, right? This right here. In some sense, here's where it goes. dx, dy, dz is partial xyz partial rho phi theta d rho d phi d theta, right? And I have to put absolute value. That's a mnemonic to remember the change of variables theorem, right? I could keep talking and make it more confusing. Does that answer your question? Yeah. Did you see my point about where it's desirable not, if you want to calculate the Jacobian and you have one transformation given in one direction, but you're asked to calculate the Jacobian of the inverse transformation, you don't actually have to find the inverse formulas to find the Jacobian. You can just calculate the Jacobian and invert, take the reciprocal. It's easier. What was the next question? No question? No question? So that was one thing I wanted to tell you about, because I forgot to mention that one year, and I inadvertently asked a question like that, not on purpose, mind you, just happened to reverse the orders of x, y, z, and u, v, w without thinking, and it made for a very nasty problem. Because sometimes, even for relatively simple formulas, it's not that much fun to try to solve these for x, y, z, is it? I mean, you could try, but u equals what function of x? I mean, it's nasty. Let's see here. Let me try to find a good polar coordinates example to do for you guys. Come on. Oh. Well, I think what I'm looking for is sitting on the chair over there, of course. Good job. By the way, if you want more examples of Jacobians, look at page 309 of the notes. There's a bunch of them there. Stooge. All right. So we'd like to calculate this integral. I equals the integral from 0 to 1, integral from 0 to 1 minus x of the square root of x plus y times y minus 2x quantity squared dy dx. Actually, the question is more properly to solve this integral by making an appropriate change of coordinates. Now this one, a lot of the the substitutions we've done so far have been based on just looking at the bounds and going, aha, it's spherical, aha, it's cylindrical, right? This one, we're going to make a change of variables, which is really just tailored to deal with the integrand. So to make this integrand simpler, we can make a linear change of coordinates. Basically, we're just going to let this thing be u and let this thing be v. So, in other words, we have u is equal to x plus y, and we have v is equal to y minus 2x. So what we're going to do, and it's going to take me a little work, but eventually we're going to figure out how to rewrite this integral. In terms of different bounds, we'll have the square root of u times v squared. We'll need the Jacobian, right, of, how's it go, xy uv, right, du dv. So I need to fill in, I need to figure out what the bounds are. I need to figure out what the Jacobian is, all right? I suppose we could just, we could use the trick I was just talking about to calculate the Jacobian, right? Do you want to do that? We can do that. But we're actually going to need to solve this for x and y anyway, so let me just get to it. If you subtract these equations, what does it give you? I get u minus v is equal to what? 3x, right? So therefore x is equal to 1/3 u minus v. So there's one of my inverse transformations. And what else do we have? What's y equal to? Y is equal to, u minus x, right? From the first equation, which is what? U minus 1/3 u minus v. So therefore y is equal to, looks to me like 1/3 of 2 plus v? Or rather 2u plus v. Do you agree or disagree? You guys can solve 2 equations and 2 unknowns, right? Okay. So what's the Jacobian then? I need the determinant of, let's see here, xu, yu, xv, yv, which is the determinant of 1/3 minus 1/3, 2/3, 1/3, otherwise known as 1/9 plus 2/9, aka 1/3. All right, well, at least one of these things wasn't too hard, right? So we just figured out that this is 1/3.
Meaning it goes up front.
Right. Well, I'm just going to leave it like that for the moment. Now, the other problem we have to figure out is how does the xy transform to uv, right? What does this thing look like in x and y? Looks like x goes from 0 to 1, right? But what does y do? So we've got this region, right? Fun fact, linear changes of coordinates take triangles to triangles in such a way that the edge of the original triangle becomes the edge of the new triangle. So basically, to figure out where a triangular region is mapped under a linear change of coordinates, all you got to do is map the vertices and see where they go and then connect the dots. Simple as that. So I got 3 dots, right? First of all, where does 0 map to? 0 maps to, let me call these points A, B, and C. So A maps to A prime, which is 0 again. Where's B prime? So 1, 0 maps to u equal to 1, v equal to minus 2. So what did I just say? 1 minus 2? There's B prime. How about C prime? So I have to, what is C? C is the point 0, 1, right? So I put y equal to, so I get 0 plus 1, comma, 1 minus 2 times 0, which is 1, 1, right? So it looks like C prime is here. And so, and then the points in the interior map to the interior. You can prove this. We'll just use it though, okay? So that's the transformed region. So the change of variables needs to do the integration over the red triangle. How do I express those bounds in the UV coordinate system? I'll do the easy one. How about V? What's V stuck between? In other words, what's this equation here? All right, I'll take V equals to U, but yes. How about the other one? V equals minus 2U. Let's take that out for a spin. If we put in U equal to 0, we get 0. Good sign. If we put U equals to 1, we get minus 2. Yeah. I like. Okay, so we have 0 less than or equal to U less than or equal to 1, and we've got minus 2U less than or equal to V less than or equal to U. That is how to describe that triangle, right? So the bounds, we should do what? First of all, we should reject the du dv. That's a stupid way to do this integral, right? So we should reverse those. We should do v first and u second, right? And the v integral goes from minus 2u to u, and the u integral goes from 0 to 1. So we integrate from 0 to 1. The square root of u times 1/3 1/3 u cubed minus 1/3 minus 2u cubed du. And there's a third that I should pull out front, right? Per Mr. Gibson's instructions. Agreeable? I'll take that under advisement. So 1/9 integral from 0 to 1. And we've got what? U to the 7 halves? But how many of those do I have? I've got 1 minus a minus 8. I got 9. So I'll take your 1/9 and I'll take my 9 and I'll make it into a 1. Wasn't it? It's almost like this problem is pulled out of some classic calculus book or something. Let's see here. So 7 halves plus 1/2 is? I mean, 7 halves plus 1 is what? Duh, 9 halves, right? 2/9 is the answer, yes. Woo-hoo. That was example 6.5.11 in my notes. That's on page 310 to 311. But again, example 6.5.11. I've got 2 Ks in acknowledgement for some reason. Hey, before you make too much fun of my notes, you should remember I'm doing this without a spell checker. Okay, so keep that in mind. Anyway, this is from Thomas's Calculus, the 10th edition, page 1040. So, Thomas's Calculus it's a good calculus book, right? Hey, does one of you have my calculus book, perchance? Lost it. I do not know where my Salas and Hilly's gone, which is unfortunate because they're not exactly cheap, right? Well, if I ask the textbook folks again for one, they'll let me have it. But all right. By the way, the example 6.5.14 is the triangle one that we did yesterday, but I got stuck on the integration. The thing I needed to remember was that sine theta plus cosine theta can be rewritten as the square root of 2 times the sine of theta plus pi over 4. See, if you know that, then the integral of d theta over sine theta plus cosine theta squared just becomes the integral of 1/2 cosecant squared of theta plus pi over 4, which isn't bad. So that was the necessary integration to finish that hideous triangle problem I started. It does work out to a half. Sorry, guys. I'm trying to find one that's like that problem in your homework with the polars, but it's not the same exact problem. Do you guys have a problem in the book in mind that I could work that would be similar? What's the homework problem? You guys remind me. Okay, go for it. What is it?
17,
Yes, but what is it? Yeah. What's the problem?
Double integral.
Mm-hmm.
1/2 1 for the outside one.
Mm-hmm.
0 to radical 1 minus x squared.
Mm-hmm.
dy dx.
dy dx?
Yeah.
That's kind of the opposite of the kind of problem I was looking for. I want one that involved, that's given to you in terms of being the interior of something bounded by some polar coordinate expression, like,
No. This one,
I mean, I can do this one. So x is going between 1.5 and 1. So the square root of 1 minus x is this thing, right? I'll finish the problem you gave me. X goes between 1/2 and 1, right? So what you're looking at is this thing. That's actually kind of a nice problem. So how would you do that in terms of polar coordinates? How? That's not a problem. Not a bad problem, actually. I'm gonna stick with it. It's not as trivial as it first looked. So to figure out polar coordinates, what you do is you draw rays, right? And you figure out where does the ray intersect as the inner radius and outer radius. Outer radius is easy. It's 1. And theta goes from 0 to something. I'm not sure what the something is, but the outer radius is 1. So I'm going to do r dr d theta, okay? I argue that this and that are easy to see. Now, what you got to do is go, okay, so if x is equal to 1/2, well, that's equal to r cosine theta, right? Which makes what? That makes r, the inner r, actually equal to 1/2 cosine theta, right? All right, so got to face the music. There it is. That's the inner radius. What's the outer? I mean, and what does the angle sweep from? I argue that the angle sweeps down here, theta equals to 0, all the way up to that point right there, right? And so what is that? What is that angle? Yeah, I mean, how do you want to figure it out? I mean, it's up to you. What do you want to do?
cosine of theta is 1/2.
Right. Yeah, 1/2 is equal to cosine theta at that point, because it's on the circle as well. It's where r is equal to 1, so the r goes to 1 in the previous formula. And I think I agree with Luke. Pi over 3? Yeah. So there you go. Integral from 0 to pi over 3. Oh, that's not too bad. Fine. I thought this was going to be more exciting. 1/2 r squared evaluated from 1/2 cosine theta to 1 d theta. So what does that give us? I thought I was actually going to have to do a secant integral. Nothing so much fun. Not so much fun. This is 1/4 cosine squared, right? Minus. Why did I get the third there? Because I'm an idiot. There's no 3. 2. Duh. 1/4 cosine squared theta minus 1, right? Oh, yes. I'm sorry. Eventually I'll learn how this works. Let's see here. 1 minus 1/4 cosine squared theta. It's good I make these mistakes on purpose for you guys to learn. It's just an example of my pedagogy. Let's see here. Ha, 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 ha. All right. Hey, look at that. That's let's rewrite that as something more interesting. 1/2 minus 1/8. What is that? That's secant squared theta, yeah? D theta. Oh man, how do we integrate secant squared? Yes, secant squared's integral is tangent. It's a basic integral. If you don't know it and you try to derive it, you're in a bad place. But we've all done it at some point or another. Yes, this in fact integrates to tangent theta, so we get pi over 6 minus 1/8 tangent theta evaluated from 0 to pi over 3. I believe we agreed that the tangent of pi over 3 was square root of 3, so we've got pi over 6 minus the square root of 3 over 8.
Whatever number that is.
That is his number. This was number 11. I'm afraid you could check the answer. Is that it? Oh. Any questions about this one before I erase? Don't just try to make up these problems. Like, this is carefully constructed so that it works out nicely. I have just tried to make these up on the fly. Yay. All right. Oh, let's see here. Try to think of something. How about this? Don't look at this. Hmm. Hmm? Hmm? Hmm. Hmm. Very good. Okay, I think you're starting to see through my ploys. Now there's ways of disguising this better, but as you read through my subterfuge rather quickly. That's good. In other words, this is a circle, right? And it's centered at 1, 0, radius 1, so it looks like this. That was supposed to be a circle, yes. And so you want to calculate the integral over that, right? This is a great problem for me to introduce a new idea for you. We have talked about polar coordinates centered at the origin, right? Because they're convenient to our purposes. Where should we make coordinates up for this problem? How about this? X is equal to, let's say x bar is equal to x minus 1. So that means when x is equal to 1, x bar is equal to what? When x is equal to 1, and then we'll let y bar equal to y. Right, so that makes this point right here where x bar, y bar is equal to 0, right? And then I would suggest to you we can say x bar is equal to s cosine beta and y bar is equal to s sine beta. These modified shifted polar coordinates based on that new point, right? And if I calculate the integral of x dA, it's pretty clear geometrically I can go from